Hello, everyone. I'm Antoine Vastel from Datadome.
And I'm Konstantina Kontoudi. I'm a lead data scientist at Datadome as well.
And today we are going to talk about bad bots and how we can detect distributed attacks using streaming-based outlier detection and a machine learning approach called SliceLine. Okay, but before that, let me give you some context. You may not all be familiar with bad bots, but I'm pretty sure that you are all familiar with what you see on the screen. So these are called CAPTCHA, and I'm probably sure that you see them every time you're browsing the web to prove that you're human. Websites and mobile applications are asking you to select the crosswalks, the bicycles, the traffic lights, and it's become so popular and so horrible at the same time that you can find a lot of memes about it everywhere. You know, everyone is really stressed, like, do I need to select the square that includes 1 millimeter of the fire hydrants? I don't know. Do I need to select the square that contains 1 millimeter of traffic lights? I don't know. Would a bot do that? Would a human do that? What will make me more human? Okay. And all of this because of bad bots. But can we detect bad bots without CAPTCHA? Because I think we can all agree that this is a really bad experience for human users, and at the same time, it's not really secure anymore because of techniques like captcha farms or image and audio recognition techniques. Before we explain our approach to detect distributed bad attacks, I will give you some context about bad bots, how they can be created, the type of attacks that they conduct, and the kind of signals that we can use to detect them. First, what's a bot? It's a program to automate actions. It can be used for positive purposes, like automating website testing, indexing the web, like Googlebot. But it can also be used for nefarious purposes, to test a batch of stolen credentials, generate fake video views and retweets, for example. What can bots be used for? They can be used to conduct credential stuffing attacks, for example, to steal batch of user accounts. They can be used to do DDoS attacks, to make a website or a mobile app slow or unavailable. They can be used to test stolen credit cards, for example, to verify if the credit cards are still valid and sell them for a higher price, or to manipulate votes, increase number of views, retweets, etc. How can I create a bot? Different techniques. You can use simple HTTP clients. So pick your favorite language, Node.js. You can use Axios, Python. You can use AO HTTP or request library. The good thing with this kind of bots, let's say, is that they use not a lot of CPU and RAM resources, but they don't execute JavaScript. And also, they may have inconsistent HTTP headers, inconsistent TLS fingerprints. You may use more advanced technologies like automated browsers. So you can automate Chrome, you can automate headless Chrome using Puppeteer, using Selenium, using Playwright. So a lot of libraries that make it really easy to instrument a browser nowadays. These bots require more computational resources because they create a real browser, but from an attacker point of view, it enables you to execute JavaScript natively and to support all the native browser APIs. Also, a benefit from attacker is that they get consistent HTTP headers, consistent TLS fingerprint, but there might still be some inconsistency that can be used to detect them. How can we detect bots? When it comes to bot detection, there are a few families of signals that you can leverage using machine learning or using rules. You may want to use signatures or fingerprints. This can be fingerprints collected on the server side or on the client side. So on the server side, it can be any HTTP header, any TLS fingerprint, any TCP fingerprint. And in the browser, it can be any browser fingerprint collected using JavaScript. Then you can conduct behavioral analysis using mouse movements, for example, or the way a user is typing on his keyboard. But you can also collect behavioral signals on the server side by analyzing the time series or the browsing patterns. For example, it may not be normal to do add to cart before viewing a product. That's the kind of thing that can be expressed using machine learning or rules. You can also have different kind of reputations, like IP address reputation, session reputation, or look at the IP address was it used as a proxy recently. And finally, all kind of contextual information, like the country, is it consistent with the website targeted, with the time of the day. To show you an example, I'm going to show it. It's really simple. It's with Selenium. Originally, it was created to test websites, and it's still used. It's still really popular. And Selenium and Chrome, when you execute a Chrome driver, it will, one of the side effects, it's not really visible, but it will inject, it will have a side effect. It will inject the document.$cdc variable in the DOM, in the JavaScript context. And so, as a bot detection company, what you can do is just look at the presence of this attribute. And if you have this attribute, you're a bot. Okay. As you can imagine, attackers will try to erase it from their fingerprint to make it more human. So what are the kind of bypass techniques used by bots? They can forge everything, basically. You can't trust anything because it comes from the client side. So the HTTP headers that are sent, they can be spoofed. The JavaScript fingerprint can be spoofed. Everything can be modified. For example, you can change your TLS fingerprints using libraries like CycleTLS. It's really easy to use. You just give a user agent, and it will generate a consistent TLS fingerprint that you should have if you had this user agent. You have a lot of databases or library also that collect a lot of fingerprints from real users that you can use to apply on your bots, and so that your bots have consistent configuration, consistent GPUs, consistent countries, time zones, etc. And even for the bots that don't execute JavaScript, it may seem simple to detect, but they can forge your TLS fingerprint, but they can also forge the JavaScript payload used to verify the execution of JavaScript. Bots will also distribute their attack using proxies. It enables them to avoid IP-based rate limiting. So for example, I'm going to block you if you make more than 10 login attempts per IP. But because they use thousands of proxies, suddenly they're not blocked anymore. They can use residential proxies to avoid rate limiting and avoid reputation-based detection. Basically, they will use IP addresses that belong to well-known ISPs like Comcast, AT&T, Verizon, and it will look like normal traffic. You won't find it suspicious because it's not linked to any data center autonomous system. And they can use even better proxies that are located in the same countries as the website they target, and in this case, it will enable attackers to bypass geo-blocking, for example. And you don't even need to be a really good bot developer. You don't need to be an expert in fingerprinting, proxy, all these kind of things. You can just use generic automation frameworks. For example, if you want to automate Chrome, you can use Puppeteer, but it's really easy to detect it. So people have developed Puppeteer extra cells, which enable you to modify your fingerprint, integrate natively with CAPTCHA farms, etc. So you just apply the changes that they recommend, and suddenly you almost look human. And if you don't like Puppeteer, you can use undetected Chrome driver if you prefer to stay in the Selenium world. And it does the same thing. It will erase most of the differences that you would find between a headless automated browser and a real browser. But in addition to generic bot frameworks, there are also more specific frameworks that make it easy to conduct attacks like credential stuffing. For example, OpenBullet 2 is really popular and makes it really straightforward to conduct large-scale credential stuffing attacks. It comes with all kinds of features like a proxy or configuration with consistent HTTP headers, etc., CAPTCHA farms. So it's really easy to conduct credential stuffing attacks. Okay, so in 2023, we see that bots, they will distribute their attack to appear more human. They leverage thousands of residential proxies, and they have a lot of ways to change more or less consistently their fingerprints to escape detection. how can we block these ever-evolving and distributed bots without using CAPTCHA and annoying real human users? And Konstantina will explain it.
Thanks, Antoine. So before going into the algorithms that we're using to detect distributed attacks and block them, I'm going to explain to you the use case and show you how you can conduct first a manual analysis. So let's say that you want to protect a website, and you have an analyst looking at an interactive tool like Kibana. You're looking for the traffic of the website, and you see that there is a sudden spike. So you suspect that there are some bots that are attacking this website, and you want to find out what is the characteristic of the bot traffic. So one simple thing that you can do is take the traffic and split it by different characteristics. For instance, here I'm showing that you can split the traffic by the list of headers, by the list of user agents, autonomous systems, and countries. And what you most likely see is that there are some specific values of these characteristics that appear at the time when the attack started. So this will allow you, like for instance here, we can see that the country that is Russia, I think, and the user agent is the one with the purple line. So when you're looking at this traffic with your eyes, you can derive a rule and say, okay, this is the rule that I found. If you have a rule engine that you're using to protect your website, you can add it to the rule engine and block this traffic right away. But all of this is manual, and you need a lot of manual work and manual investigation to find the rule. So what we did is we found a way to automate all of this. So we have two basic steps. The first one is to detect automatically the distributed attacks. And the second one is to make an analysis and find the rules so that we can dynamically generate rules as the attacks come in. So let's start with how do we detect distributed attacks. So first of all, we have the number of requests over time, obviously. But on top of that, we compute several aggregations, like the number of unique user agents, the number of unique IPs, the number of unique sessions. And this allows us to detect distributed attacks because even if there is no spike in the number of requests, we can see that there is a spike, for instance, in the number of IPs or in the number of countries that all of a sudden come and attack the website. So it allows us to detect not only distributed attacks that have a high number of requests, but also low and slow distributed attacks coming from several IPs, for instance. So these aggregations will make up time series, one for each aggregation, and we apply an anomaly detection on those time series, which is based on the Z-score. So just to give you an idea of how it works is you keep a rolling window on your time series. On this window, you can compute the mean and the standard deviation of your time series. And then for every observation that comes after the window, we can go and check and see if this observation is extreme with respect to the mean value and the standard deviation in the window. This is basically what is anomaly detection based on the Z-score. So if you find that this value is extreme, then you understand that an attack has started. And you can push an event to your system and say, we have an attack for this customer if you're protecting several customers, and this is the start time of the attack. And this algorithm, we implemented it in Flink, which is the streaming engine that we're using. So this is an example of time series that we have. So on the top left, you have the number of requests, the number of user agents, the number of IPs. On the bottom, the number of countries. And you see that sometimes not all of them have a spike at the same time, but it's sufficient to have just one time series with a spike to understand that there is something going on with this in this customer. And then you get your attack start time. And this is basically the only input that the algorithm needs to find rules and be able to block the attack afterwards. So how are we going to do the analysis? So now that we have the start time of the attack, we can wait just a little bit so that we can collect two separate data sets. We have the green data set, which is the traffic before the attack, and which is in majority normal, meaning that it's not coming from bots, it's not suspicious. And then we have another data set with the traffic during the attack. And this will typically contain a mix of bot and normal data. So keep in mind that we have these two groups of traffic. So if we go back to the plots I was showing you before, so we kind of done this analysis manually when we said, okay, which is the value that arrived just after the start of the attack. But only now we know the exact time when it started because we applied the anomaly detection. So that's done. So now we have to find a way to generate rules in an automatic way. And for this, we're going to use an algorithm which is called SliceLine. So before showing you how to use it to generate rules in practice, I will introduce you into the basics of this algorithm. So this algorithm was proposed not so long ago to debug machine learning models. So this was the original purpose of the algorithm, is you have trained a machine learning model, and you want to find in which cases the model is underperforming. So let's say that you have a data set of requests, just as a toy data set with just the country, the user agent, and the IP type. You trained an algorithm, and you are able to see what is the error the algorithm is making for every row in your data set. Let's say you have it. And then you want to find the slices in your data set, meaning a subset, a set of rows in your data set, where your machine learning algorithm is underperforming, meaning that it has a high error. So this is what this algorithm allows you to do, is to find those slices. And those slices in practice, they are expressed as a conjunction of conditions. So here I'm showing two examples. You can have a slice where you say the country is Germany, and you will get an error of 0.9. Or you can have a bigger slice with the two lines, the third and the fourth, the two rows where you have a different set of conditions. And this is, in essence, what is a slice. But here, in our use case, we don't have such a model. And I'm not going to talk to you about training a machine learning model, actually. So here is the twist. So we can take this algorithm, and instead of using the error of a machine learning model, we can just use 0 and 1 groups. So what we do is we take the human traffic, and we assign it a group 0. We take the suspicious traffic, and we assign it the group 1. In this way, since the algorithm is trying to find a subset of samples where you have a high error, what the algorithm is going to do is it's going to find rules that target your group 1. So in our case, this is the traffic just before the attack and the traffic during the attack. But this is something you can adapt in any cybersecurity use case where you have two distinct data sets, and you want to find rules describing one of the two data sets. So the group you want to target, you assign it group 1, and the other group, you assign it the group 0. And the algorithm will find the rules for you. So now, before I show you the code that you need to write to do that, I would like to give you a glimpse of how it really works, but without going into mathematical proofs or details, but just to give you an idea of how it can work. So the algorithm is searching for slices with large errors, as I said. And for this, you need a way to quickly compute the error, the average error for a specific slice. To do that, it uses matrix algebra. Why? Because if you manage to write this operation using matrix multiplication, for instance, you can use all the existing implementations which are highly optimized, even for distributed computing or GPU-accelerated implementations of matrix multiplication. And thus, you can have an algorithm that scales without much effort on your side because it's already implemented for you. And on top of that, it uses some pruning techniques so that it can reduce the search space. Because as you can imagine, the more attributes you have in the dataset, the more combination of conditions you can do. And this space that you need to search is exponential. But the authors of the paper have found some heuristics to reduce the search space without accessing the data all the time, which dramatically improves the performance of the algorithm. So I'm not going to go into the details of all those points, but I'm just going to explain to you how you can use matrix multiplication to match rules. So let's start with the beginning. So we have the toy dataset that I showed you before. And the first step is to do an encoding of the dataset. So the encoding I'm talking about is one-hot encoding. It's something that is used all the time in machine learning for categorical features, meaning features that have values which are distinct, not continuous values. So one-hot encoding, what it's going to do is going to take a column with different distinct values. Let's say country here, it has 3 different values. And it's going to create 3 different binary columns where you will have one where the condition country equals FR is matched and 0 otherwise. And then you have another column for Germany, another column for China, and so on and so forth. So in this way, the features of your data set that were categorical now are expressed with a binary matrix of zeros and ones. And in the same way, you can also describe rules with binary vectors. So in this space where you have every conditions written out, you can have a vector representing a rule. For instance, if you want a rule to say country equals Germany, you will put 1 in this column and 0 everywhere else. This is the first line. And for the second, which was user agent equals Chrome and IP type data center, you will have 2 ones in your vector. And so you have 2 vectors here that each one of them represents a rule. And everything is binary, so it doesn't take so much space, and also it is sparse. So you can also use sparse matrices to store this data. So then, having this data set in this format and the rules, which I just transposed to make them, you can do matrix multiplication to understand which row matches which rule. So when you do matrix multiplication, you will effectively get, for instance, the first row multiplied with the first column, representing the first rule. And you find a 0. So the first row with the second column, you find 0, so it's in black. Then you have in red the result of the multiplication of the second row with a rule matrix, etc. So what you can see in the result is that the third row matches both rules, whereas the fourth row matches only the second one. So I'm talking about the rightmost matrix over there. So this simple operation allows you to find which row matches with which rule in just one mathematical operation. So then, as I said, SliceLine, when it's doing the algorithm, is repeatedly computing the average slice errors. So you have the error, you have the matrix which tells you which row matches with which rule, and it's very simple to compute now the error of a slice just by multiplying the error vector with a matrix L, which I called L, which is the matrix that shows the matching of the rules and the rows. So in this way, when you do the multiplication of the error with this matrix, you get the total error for a specific rule. And then, in the same vein, you can multiply with the identity vector and get the count, because matrix multiplication will effectively count how many ones you have in every column. And then just by dividing it element-wise, you will have the mean slice error. And this is actually the computation that SliceLine is repeatedly doing. So it starts with just one condition. It spans all the conditions, computes the error, decides if it needs to go further in the search space, and then does that with 2 conditions, 3, and so forth. So this is a parameter that you have in the algorithm to tell him, okay, how many conditions you want to have at most. So this is, if you have something to take away from this, just what I wanted to show you is that matrix multiplication can help you evaluate rules like very effectively. So the authors of the paper, they provided an implementation in R of the SliceLine algorithm, and we took the implementation and rewrote it in Python, and we open sourced it. So I invite you to go check our GitHub repository. In the process of implementing the algorithm in Python, we rewrote some part of the code that was using for loops with matrix multiplication, again, to make it more efficient. And so this allowed us to leverage the NumPy library. It's a Python library which contains efficient implementation with C++ code underneath. And also, the framework is compatible with pandas, which is used for data analysis, data science in Python. And so in this way, we speed up the implementation by more than 1,000 times. So the good thing about all of this is that all this process is just a mathematical algorithm, and the rules that come out of it are completely agnostic to the rules engine that you might want to use. So you can transform the result in any format you like and use it in your own system, in your own use case. So let me show you what is the code that you need to write. So here we took an example data set from a French e-commerce website. In order to create the 2 distinct groups, we took requests that have a very old session, which are in majority coming from humans. And then we created another data set with suspicious traffic. And these were requests coming from non-French speaking countries, because we're talking about an e-commerce website which is French. And also that use data center IPs. So in this way, we created this data set with several features, and we assigned the group. Group 0 for human traffic, group 1 for suspicious traffic. So this is a pandas data frame, in practice, what I'm showing here. And so to run the SliceLine algorithm, you just need 2 instructions. You just need to instantiate the SliceFinder class, which is what is the class implementing the algorithm. And then you just call fit to it with your data and with the group as a target. And that's it. You can compute the slices in this way. So there are some parameters, like as I said, the number of conditions that you need to have, or the number of rules that you want to get. I won't go into the details. We can discuss about it afterwards if you need. And so this is the code snippet on the upper left. And then I'm showing you how easily you can convert the result in any format you want. So here you can see that the algorithm found that the bot traffic was coming in majority from Germany, because actually we biased the dataset by selecting traffic coming from non-French speaking countries, and in fact it's consistent with what we wanted. And it found slices of different size, so you can see the first one is just country Germany, and the other ones are more restrictive and they are a bit smaller. But this is how easy it is to use. So don't hesitate to have a look. So now I'm showing you a real-world attack that we blocked using this methodology. So you have a blue line, which is the traffic on one of our customers' websites. So this is the login endpoint. So we're talking about the credential stuffing, and the customer is a gaming platform. So you see that the blue line, there is a small spike that the anomaly detection algorithm captured, and then this triggered an analysis using SliceLine. So then we found a rule, which is represented by the orange curve, which matched exactly the excess traffic that we saw on the customer's website. And then we used this rule to actively block traffic matching this pattern. And within a week, we blocked more than 3 million requests. So if I show you now the same attack, but from another viewpoint, where instead of showing you the number of requests, I'm showing you the number of unique IPs, we counted more than 187K distinct IPs that were used by the attackers for this use case. So this is all I wanted to tell you about, me and Antoine. So if I want to summarize, so we've talked to you about an algorithm to detect distributed attacks, where we used aggregations followed by anomaly detection. We used SliceLine to generate rules and find the signatures of the attacks. And I want to stress out that this is an effective algorithm against bots that adapt. We don't need to know beforehand what is the signature, what the attacker's signature looks like. We detect that something is happening, and we can generate rules on the fly and block the traffic right away. And also the last point is that SliceLine can be applied to other security use cases. And if you have a rules engine and 2 groups of data, you can use it to generate rules. Now, if you want to contact us, this is our contact information. And if you want to come by the booth, we are in the booth number 12. So if you have any questions, go ahead. Sorry, can you?
Could you use a mic so that everyone can hear the question, please?
Okay, for example, I have a data set, right, which is offline now, okay?
Yes.
And because before that, I did not have this, this tool, right? So can we use your tool to analyze that data and find out whether there was any anomaly in that or not?
You mean the anomaly detection part?
Yeah, so previously there was nothing, okay? I just collected the data. There was no prevention, okay? Now, I know like you have a tool, right? So can I use your tool to analyze the data which I already have?
Yeah, you can do it afterward. So like in our case, we do it live. So we have the outlier detection part and the rule generation part. Let's say in your case, as a human analyst, you know where the attack started. You could take all your data 1 month after the attack and say, this is, the signatures or the signals I collected before the attack. You know when the attack started without using any algorithm, just because you saw it. So you can split your data into 2 groups manually, with a program, and then apply SliceLine using Python afterward, whenever you want. And then you can specify how much, rules you want to generate, the number of, signals that you want to be taken into account. And you can completely do it after the attack occurred, yeah.
Thank you.
But if I may add something, it doesn't always have to be before or after. You might have some other split in your head of, this is suspicious, this is not suspicious, and apply it in those 2 groups. You just need to have 2 groups. No need to have like before, after.
So the data can be in any form, right? For example, TCP dump also, or you just need the data in a specific format?
So the reason we introduced a pandas feature is because pandas is really convenient. It's compatible with a lot of data formats, so you can read a lot of data format and convert them to pandas. But behind the hood, we are using vector representation. But you can use Panda to read a CSV file or a log file as long as you have a way to parse the data. And then we automatically, I don't know if the library currently binarize the value or not, but
Yes, yes.
Okay,
it does.
yeah, it's perfect. So yeah, we take care of transforming the data to one-hot encoding so that it can be handled by the algorithm.
Thank you.
Any other questions?
Hi, I'm Louis. There are some web application firewall that deals with anti-distributed DDoS attacks. Is your solution similar to those kind of solutions?
So yes, we are not only doing DDoS attacks. Basically, we operate at layer 7, so only layer 7 DDoS attacks, but also all kind of bot attacks. So it can be scraping attacks, credential stuffing attacks, carding, scalping attacks, where bots are trying to buy limited edition products. So the goal is really to detect automated form of traffic.
So in this aspect, what's the differentiator?
With a WAF, you mean?
If let's say those web application firewalls, they also have this anti-DDoS capability.
So we take more signals into account. Basically, I would say we also take the client-side aspects using JavaScript or using SDK if you have a mobile app. And then all kind of behavioral features that are more complex than simply using rate limitings. We can discuss after, because I don't want to talk too much about the product now. It's not, yeah.
I think there was someone else who had a question. No?
Hi. Our question about for those tools that can mimic the mouth movement, or like human behavior, and the attack is not a large scale attack. Is it possible to use this kind of tool to detect?
So is your question, can we apply it on mouse movement signals?
Yeah.
Yeah, actually, we are doing it. So basically, as long as you have a data set of human mouse movements, these are numbers, so we need to convert them to discrete values, group them in buckets of numbers. And then if you have something that you know is mostly bot and something that you think is mostly human, you can run the algorithm on it. And let's say you have a feature which is the mouse movement speed, another feature which is the duration, another feature which is the number of mouse events. Then the algorithm may learn that if you don't have a lot of mouse events and a high speed, you may be more bots than human. So you can apply it as well on this kind of signals.
Okay, thank you. So next question is, have you faced any kind of very sophisticated tool like that, and how you overcome, how you defeat that kind of tool?
So you mean like tools that will generate realistic mouse movements?
Exactly like human.
Yeah.
Record whatever we're doing with a data set, try different data set.
Yeah, so in the case where an attacker would just replay human movements, of course, behavioral analysis won't be really useful because it will be the same as for legitimate human users. So that's why when it comes to bot detection or fraud detection in general, it's more like we have a layered detection approach because some signals won't be useful, not all the time. So for example, let's say you want to use TLS fingerprints. It will be really efficient against bots that are not using real browser or that lied about their identity in their user agent. But let's say you are using a real browser, a real Chrome automated, you will have a consistent value. So it's not useful. That's why we need to combine different things like reputation, behavior, and at different levels. And the good thing with the approach, this one in particular, is that most bot detection techniques look at the session or the IP to verify if something wrong is going on. Here we analyze the whole website traffic to see if something bigger is happening in the distribution of the data, and then we try to understand why it changed. But yeah, it's important to have different kind of approaches. Not a single approach can solve everything.
Thank you.
Okay, thanks a lot. We have 1 minute left. Thanks for your questions.